Okay, so far we've been using Riemann sums just to estimate in section 5.1 areas and distances, and in section 5.2 signed areas and displacements. Okay, and generally when we've been doing it by hand, we've been doing a bad job. Okay, because we've been using 3 rectangles or 4 rectangles. We haven't been chopping things really fine into lots of really small pieces. And that's okay, because we were just getting familiar with this concept of chopping things up into little pieces to approximate with a Riemann sum. I know that ultimately I'm going to be taking a limit as the number of rectangles goes off to 0, and more importantly, as the base of those rectangles shrinks to 0. When I do that, I'm going to need to use this summation notation. If I have 3 rectangles, I can write first plus second plus third. If I have n rectangles, and I haven't specified exactly what n is, because n is a variable, and I'm going to take the limit as it goes to infinity, I'm not going to be able to write out first plus second plus third all the way to the nth. That's only practical if I know exactly what n is, so I'm stopping at a particular value of n, which inherently means that I'm not taking the limit, okay? And if that's small. If I have a big number, I don't want to have to write it out term by term. So we haven't been using the summation notation a lot because we've just been practicing with relatively small Riemann sums. But as we move towards taking the limit of a Riemann sum, we're going to need to get comfortable working with this summation notation. So, just a little bit of vocabulary. Okay, I here is my index. That's just keeping track of which term I'm talking about. So it's a variable, and it takes on integer values from the initial index. So in this case, the initial index is 1 to the final index. And in this case, the final index is n. Now, for the purposes of our Riemann sums, the initial index will always be 1, because we're always going to start with the first rectangle. It doesn't make sense to chop things up into 50 rectangles and say, you know what, let's just ignore the first 2 and let's start with the third. We're always going to start with the first rectangle. And we're always going to end with the last one. And if I chopped things up into n pieces, I would have n rectangles, so the last one would be the nth. Okay. For general summation notation, there's nothing that says that that initial index has to be 1. You can have sums that start with the second or the third term. In some contexts, it makes sense that you don't care about the first couple of terms. But for our Riemann sums, we'll always be going from 1 to n. This initial and final index also have some names. This initial index is called the lower limit of summation. And you might see that word limit and say, oh, what does that have to do with limits as I know and love them? Or maybe as I know and hate them, but I hope not. I hope you love your limits. Okay, well, it does have some connection to limits as we've seen them before, but I think the best way of thinking about this is it's just one of those times when we use the same English word in 2 different contexts to mean 2 different things. Okay, so the lower limit of summation is just the initial index, or the starting value for the index. Okay. Similarly, the number that's up here is called the upper limit of summation, and that just means the ending index, or the last value that the index takes on. Okay. A sub I, that's just going to be the ith term that I'm adding up. And this symbol here is a sigma. I spelled it with a capital S because that is a capital Greek letter sigma. And it just says add everything up. Start when the index is 1, take A1. Then count to n. So the next index would be 2, take A2. So this basically just means A1 plus A2 plus A3 plus ... plus AN. Okay, so we're going to be working with these a lot, and so there are a bunch of rules of sums that we're going to need to familiarize ourselves with. And my guess is you're already familiar with these rules, but you might not be familiar with using them in conjunction with the sigma notation. So we have some rules for sums. And for these rules, the initial index, also known as the lower limit of summation, does not need to be 1. So as I state the rules, I'm going to make the initial index 1 just because I have to write something, and because that's always going to be the initial index for our Riemann sums. But the rules are true even if the initial index is a different number, and when we look at examples, I'll often use a different starting index. Okay. So the first rule says if C is a constant, and if I have the sum as I goes from 1 to n of C times A sub I. So every term has a constant multiple of C in it, and then it's just multiplied by something. This part is going to vary depending on what I is. What this rule says is that that's C times the sum as I goes from 1 to n of A sub I. Now what I want to do is just take a look at an example so that we can see that this is actually just a rule of arithmetic that we already know, but it looks a little different when we write it in the summation notation. So let's just take a quick example. Let's say I had the sum as I goes from 2 to 4. So I'm purposely not starting at 1 just to show you that we don't have to start at 1. Okay. And let's say I had 3i squared. Now according to this rule, I should be able to factor out that 3 and get 3 times the sum as I goes from 2 to 4 of I squared. So what I'm going to do is I'm just going to write out both sums term by term. I find it helpful to just start with my initial index and count until I get to my ending index. Now, I usually will circle that index because those aren't the things that I'm adding. I'm not going to do 2 plus 3 plus 4. What I'm adding is what I get when I plug those numbers into this formula. So when I is 2, I'm going to get 3 times 2 squared, or 3 times 4. And I'm purposely being a little bit lazy and not doing that arithmetic. Okay. Plus, when I is 3, I'm going to get 3 times 3 squared, or 3 times 9. Plus, when I is 4, I'm going to get 3 times 4 squared, or 3 times 16. Now, according to this rule, that should be the same as 3 times this sum. And I know when I'm multiplying by a sum, I want to put it in parentheses so that the 3 applies to each and every one of those terms. So my index starts at 2, and I count up to my final index of 4. When I is 2, my term is 2 squared, which is 4. Plus when I is 3, I'm getting 3 squared, which is 9. Plus when I is 4, I'm getting 4 squared, which is 16. Now if I look at what I've written here, I recognize that this is just the distributive law. The distributive law says, hey, if I got a number on the outside, it's legal to distribute it to each term, so that I would get 3 times 4 plus 3 times 9 plus 3 times 16. Using the distributive law in the other direction, if I recognize that I have a common factor in each of the terms, I can factor it out, which is the direction that we'll most often be using it. It'll start inside the sum and we'll factor it out to have a simpler formula for the things that we're adding up. But that's a rule that you already knew. It just looks a little bit different when I write it using the summation notation. So that's our constant multiple rule. I should mention there is a handout on the class website, not on Canvas, but on the original class website under handouts, that gives you the rules for sums and also some formulas for some particular sums. All of this is given in your textbook as well. The handout I think is kind of useful. The rules for sums we're going to be using all the time. You got to know all the rules because you got to know how arithmetic works. Okay, but the formulas, there are about 4 formulas we're going to look at. 2 of them I'm going to expect you to know on the next exam. The other 2 I would provide for you if you need them. So you might find the formulas in the book, but you won't find the information about which ones you're expected to know and which ones I would give you on an exam except on that handout. So I'd encourage you to take a look at that at some point. Okay, let's see. I'm not quite sure how long we've been going, so I'm going to stop this video here and then continue with some additional rules of sums in the next video.